All right, we're going to go through the rest of chapter 2. The first topic is naming binary covalent compounds. So we talked about ionic compounds previously. Molecular or covalent compounds, you'll know we have a molecular compound when only non-metal elements are present in that compound. Versus ionic compounds, those had a metal and a non-metal. Molecular or covalent compounds are only non-metals. I wanted to mention as well that classification of a metalloid, that's technically a nonmetal. So for molecular compound, we have only nonmetals, including they can also be metalloids. If we have a metal present though, those are ionic compounds. Binary compounds, these contain two elements, so bi meaning two. Molecular compounds are usually thought to be easier to name. So for binary molecular compounds that don't contain hydrogen, we're going to follow this pattern. We have a prefix and then the first element name, then another prefix, the second element name with an ending in IDE. Each prefix corresponds to a certain number of atoms. So notice the prefix of di means we have 2 of those nitrogen atoms present. Pent means 5 here, so there's 5 oxygens present, so N2O5. This will be an important table to know to be able to refer back to. So we went through the general pattern. Now let's talk about these rules for the prefixes. Number 1, if a prefix ends in O or A, so it ends in one of these vowels, if a prefix ending in O or A is used with an element name that begins with an O, or it begins with a vowel, then we generally drop the O or the A from the prefix. So tetra is the prefix for 4, so carbon tetrachloride. Chloride starts with a C, so we keep tetra as its full name for that prefix. Whereas for osmium tetroxide, notice we don't write it like this. So we don't say tetraoxide, we drop that A from the prefix because this element begins with a vowel. So drop that A, tetroxide. As we talked about previously, this 1 is implied in that formula, so we never include that. So we just would say NaCl, but we know there's 1 Na and 1 Cl. So similarly for rule number 2, if the molecule contains only 1 atom of the first element, the first prefix is left out. For example here, we would not say mono-nitrogen monoxide. There's 1 nitrogen, so we do not write mono here because there's 1 nitrogen and nitrogen is the first element in that compound. If there's 1 oxygen though, and that's the second element in the compound, we do include that mono there. Notice again what we needed to do. So we dropped the O on the prefix. So we didn't end up writing monooxide. We dropped the O on the prefix because this element begins with a vowel. Notice that for tri, that prefix does not end in an O or an A, so we actually keep the full prefix here, so trioxide. So this rule applies if we have a prefix with an O or an A. But if it ends in an I, we can go ahead and write that full prefix, even though this element does begin with a vowel. Notice here as well, dioxide, so this begins with an O, and we keep the full prefix there. So this rule number 1 is primarily for elements that start with O, so the letter O. Here's an example again where we drop that O in the prefix, so monoxide. Rule number 3 can be a little bit tricky to recognize, so on rare occasions, 2 elements form only 1 kind of compound. If we do know this to be the case, we can leave both prefixes out. But again, be careful with this because silicon carbide, this means that when silicon and carbon get together, there can only be a 1-to-1 ratio. That means that we would know that this doesn't exist, for example, but again, it'll be trickier to tell what can exist and what can't exist. So this is a trickier rule to pick up on, but this can also be the case. So with this practice problem, find the systematic names of the following chemical compounds. The first really important step to this practice problem that you won't necessarily be told on an exam, for example, is that all the chemical compounds listed, they're molecular compounds. You're not always going to be told what kind of compound you are naming or working with, so you need to also get comfortable recognizing if this is amolecular versus ionic. Okay, so you're not necessarily going to be told name these ionic compounds or name these molecular compounds. So you need to be able to distinguish which one you're working with. We know that we have all molecular compounds, really importantly, because each compound contains only non-metal elements. The ones we're working with in this practice problem are also binary compounds. They contain only 2 atoms. We talked about this previously, and we'll work on this again a little bit later. And we know that polyatomic ions exist, but here in this practice problem, we're just working with binary compounds. So only 2 atoms total in the compound. That means no polyatomic ions are present here for our practice problem. So hydrogen can be unique here again. So when hydrogen is present, they have sort of their own naming scheme for these molecular compounds. We'll cover acids later on in the semester. Many compounds that begin with hydrogen are acids. Also, many important compounds that contain hydrogen, like water, we call them by their common name. So water is its common name, ammonia is the common name here. Now, if we were to name this for the classic way we would name molecular compounds, technically this is dihydrogen monoxide. So if you want to be tricky with your friends, you can say, hey, I'm really thirsty for some dihydrogen monoxide. Here's one way to summarize how we would name these molecular compounds. We're going to write the name of both elements, change the ending of the second element to IDE, place prefixes in front of each element based on the number of atoms present. The prefix mono is only used on the second non-metal in the chemical formula, and we need to avoid those 2 vowels in a row. So tetraoxide, no, we would drop that A to just have this read tetroxide. So here's our practice problem. Let's come back to these now. So these are all non-metals, so we know we have molecular compounds. You should also look at the periodic table and confirm to yourself that you understand why all of these are classified as non-metals. So use that blank version of the periodic table that's on Canvas, and really be sure that you understand where the metals are located, as well as the metalloids and non-metals. So here we have carbon and oxygen. We don't write mono out here for the first element, but we do include mono for the second. Mono would usually have an extra O here, but remember we dropped that so we don't have 2 vowels in a row. So this first one, carbon monoxide. Next we have bromine and oxygen. There is not a subscript here on bromine other than 1, so we just write bromine. We don't include that mono for the first element. Then there's 2 oxygen atoms. This is dioxide. So we can have 2 vowels here together. We're not going to have 2 O's next to one another though, like monoxide. We also won't have an A right next to an O either. So no O's together and no A and an O together. For this next one, we have bromine again. We have 2 now and then 1 oxygen. That means we have dibromine. We have 1 oxygen, so monoxide. Again, we don't change the first element. We just list it as is. So carbon, bromine, bromine here. We did add this prefix now because this has a non-1 subscript. Here we have carbon, here we have 2 oxygens. So di for 2, so dioxide, carbon dioxide. Again, all these prefixes are here on this table, so be sure you are getting more familiar with these. And you might have some of them memorized already. It's like a hexagon, for example, a 6-sided shape, so hexa is the prefix for 6. This next one has a common name to it. It has hydrogen, but let's try to write out the molecular name as well. So nitrogen and then so hydrogen, but we need to drop the ending and have it be IDE. And I'm jumping ahead here to point out that hydrogen, we changed that to hydride. So this is table 2.3 in your textbook. So nitrogen trihydride. This is also a common molecular compound that we call ammonia. Do not get this confused with the polyatomic cation that can participate in ionic bonding. Do you remember what this polyatomic cation is called? So this is ammonium. Here are our solutions. Now the next topic is predicting whether a compound is ionic or molecular. So this is an important topic here. Remember, ionic compound will have a metal and a nonmetal. Molecular will have all nonmetals. The additional exception to ionic compounds, we learned about this last time. So this ammonium polyatomic cation, this can also form ionic compounds, as well as any of the metals here in the periodic table. Then for molecular compounds, there are going to be no metals, so all nonmetals, including a nonmetal plus a metalloid. So again, practice looking at the blank version of the periodic table and distinguishing these metalloids here, these nonmetals here, and all of these metals. This is a slide you've seen before, so we remember that ionic compounds are a metal or that ammonium polyatomic cation with a nonmetal. The cation will be positively charged from the metal. The nonmetal will be the anion, it'll be negatively charged. And we looked at these examples last time where we again use that ending as IDE. So the anion ended in IDE. So be sure to use those tables and get really comfortable with changing chlorine to chloride, oxygen to oxide, etc. Now here again for molecular compounds, only nonmetals, which includes these metalloids. So it can be nonmetals or nonmetals with metalloids. We don't always name some of these common molecular compounds by their technical name. We usually refer to them by their common name. So again, you could say, oh no, did you just drink all of that dihydrogen monoxide? Which of course would just be water. This is another reminder that we'll come back with all these naming and writing these formulas where the element furthest to the left in a period, so furthest to the left and or furthest down, we list those elements first in these formulas. So that was talked about previously more in chapter 2. Here is another representation of that table we looked at. So this is table 2.4 in your book. So mono, di, tri, etc. for all these different meanings of these subscripts. Here's some additional examples. Recall that if only one kind of compound can form, then we don't include the prefixes on either of these elements. So they're not there on either of these elements, so we can just say HI is hydrogen iodide. And so again, we should feel comfortable going from a formula like this to a name like this. So now again, I mentioned that you won't always be told what type of compound, and you might be asked to name it anyway. So you'd first need to figure out what type of compound we have. Then there's different schemes for naming. So we'll go through a flow chart at the end. Once you distinguish if it's an ionic or a molecular compound, there's again a flow chart for naming all types of ionic and molecular compounds. For this practice problem, we're just going to decide what type of compound these are. I've said this a few times, we can't hear it enough, though if the compound is made from only nonmetals, we remember that's a molecular compound. If the compound is made from a metal and a nonmetal, that's an ionic compound. So in solving this problem, we need to decide if that first element here, the cation, is that a metal? So importantly, for both molecular and ionic compounds, this anion portion is going to be a nonmetal. So if we know the nonmetal is here as the anion position, that doesn't tell us if it's a molecular or ionic compound. So again, just the presence of a nonmetal here doesn't tell us which one this is. What we need to look at is the cation portion of the compound. For example, is hydrogen a metal? Is silicon a metal? Is manganese a metal? So we should be able to look at a non-colored inversion of the periodic table, find manganese. We know that is a metal. Hydrogen, it's in group 1A, but it's definitely a non-metal. Now, silicon wasn't written on this version of the periodic table, but it is on the blank version of the periodic table that you have access to on Canvas. So silicon is a metalloid. So ionic compounds have to be a metal with a nonmetal. So manganese is the only metal here. A metalloid is essentially, you can think of it as a nonmetal for our purposes now. So for naming purposes, a metalloid, you can essentially consider that also another nonmetal. So manganese is a metal, that must mean this is ionic. So this is ionic. Silicon is a metalloid, that must mean this is molecular. Hydrogen is a nonmetal, that must mean this is also molecular. So ionic, molecular, molecular, there is our solution. Now again, if we can classify these, then we can know how to name each compound. Ionic compounds are named differently than molecular compounds. Molecular compounds we just went through today, so there's different prefixes. Ionic compounds we worked on last time, and we'll do a little bit more review on it a little bit later today. So let's go into this topic now for more practice, naming binary ionic compounds. So previously we went from a formula like this, and then we were able to write out this name. We put the cation first, then because cobalt can form more than one type of cation, we had to include that Roman numeral there. Then for the nonmetal here, the anion, we took bromine and we dropped the ending, we changed that to IDE. Also, we learned last time that the net charge on the formula has to be 0. So cobalt 3 plus, bromine -1, that net charge then is 0. As a refresher of that cross method we worked on last time, this 1 comes down here for cobalt. This 3 plus then comes down here for bromine. We don't include that 1 in our final answer. We'd write COBr3. These charges net out. Bromine's a halogen. It's charged at -1. It forms -1 anions. There's 3 here in our final formula. So -3 is a charge just on the bromines. Then cobalt is 3 plus, and 3 minus. That nets out to 0. So we learned to use these parentheses here for those metals that can form more than one type of cation. What this is called, this is the stock notation. With the stock notation, importantly, you should only write in the cation charge in parentheses when the metal can form more than one kind of cation. If it can't form more than one type of cation, we don't need those parentheses. So as we talked about previously, those group 1A and group 2 elements, so the alkali metals and the alkaline earth metals, those predictably always form +1 and +2 cations respectively. Because these can only form one kind of cation, we don't need and we should not include the parenthesis there. So group 1A and group 2A, we don't write in those parentheses. Other elements that only form one type of cation, aluminum, zinc, cadmium, and also silver should be included there as well. So again, these always form +1, these always form +2. Zinc, aluminum, silver, and cadmium, those can always also only form one kind of cation. So we need the stock system for all of these that can form more than one type of cation. Iron we looked at previously, as well as cobalt. So iron 2 plus, you have to put that Roman numeral 2 here. Iron 3 plus, that Roman numeral 3. Now, something else you should be aware of with the stock system, and specifically for ionic compounds. For ionic compounds, we also have something that's called the classical system. So for example, copper plus and copper 2 plus, these two different types of ions can form from copper. So far we've learned to name that as copper 1 and copper 2 with those Roman numerals. Something to just be aware of is that copper plus 1 can also be named cuprous. Copper 2 plus can be named cupric. Where this other pattern has evolved, where the ending in OUS is for the ion with the lower charge, the ending of IC is for the ion with the higher charge. This isn't used as commonly now, but this is called the classical system. How do we know this formula has copper 1? Well, chlorine is a halogen, it always forms -1 ions. That means there must be a +1 here for this net charge to be 0. Whereas for CuCl2, this is overall then -2. That means this has to be 2+ in order for those charges to net out to 0. So we're changing the name of the anion to end in IDE. Here are some examples we've seen so far: fluorine to fluoride, chlorine to chloride, oxygen to oxide. And I did point out this table as well, so table 2.2 for some other name changes with this ending of IDE. So selenide, iodide is another common one. Bromide as well, so bromine to bromide. This is another look at that same table, so table 2.2. Let's try this problem now. So find the name and the empirical formula for each ionic compound. Here we're told what they are, but we could also infer that because all of these cations are metals. So when the cation is a metal, we know we have ionic compounds. So let's find the formula and also name these. We know pretty well now that ionic compounds, the net charge must be 0. We've seen this example now with cobalt and bromine. Looking at this periodic table, we see that cobalt can form 2+ and 3+ cations. So we know to name that, we would need to have that Roman numeral 2 or that Roman numeral 3 here for cobalt. From that cross method again, bromine's a halogen. It always forms -1 anions. We would cross that down here. Then to know which charge is on cobalt, in our final answer, this is 3. So that means that we can do sort of a reverse cross method, meaning this cobalt is a 3+ cation. So this 3+ cation came together with this -1 anion, and they formed an ionic compound. So here's how we would name that with the stock system with parentheses, with that 3 there in Roman numerals in those parentheses. So for naming this ionic compound, we just name the metal as is, in this case, cobalt. If that metal can form more than one type of cation, then we need to follow the cation's name, the metal's name, with their charge in parentheses, or with its charge in parentheses. Remember, if it can only form one type of cation, so those alkali metals or alkaline earth metals, you do not include the parentheses. So those metal cations, again, that don't need parentheses is going to be anything from group 1A, 2A, and then those different metals that can only form one type of cation. So these are those transition metals. So we know for these transition metals, they can be a little bit trickier. If they can form more than one type of cation, we have to use the Roman numerals to represent which charge that ion has. Now, if you watch the last animation from the previous video for chapter 2, it's pretty interesting when ionic compounds come together. So cobalt was originally neutral, but then it would lose 3 electrons, 1 to each of these bromines, to form an ionic compound with cobalt and bromine. That leaves this cobalt atom in a 3+ charge state. Something else to keep in mind too is that these ionic bonds, remember, they're not really bonds. So ionic bonds are not truly bonds, they're just more of these sort of electrostatic interactions or electrostatic attractions between these atoms of different charges. For molecular compounds though, we'll get to this, these bonds between molecular or within molecular compounds, those are truly bonds. So molecular compounds have covalent bonds. That's why we heard it called molecular or covalent compounds. So we'll touch on more about bonding as the semester goes on. So we already wrote out the formula for this cobalt and bromine combination, COBr3. We did also cover the name of this one as well. So this is cobalt 3. Really importantly, we have those parentheses and the Roman numeral there. Bromine is the name of this element. To change that, we need to call it bromide. Now for cobalt 2+ and bromine, if we do that cross method, again, cobalt 1, bromine with a subscript of 2. We don't include the 1, so COBr2. To name this now, we would say cobalt, and the charge on cobalt can either be 2+ or 3+, so we have to include the Roman numerals here. This is cobalt 2+, so we need that Roman numeral 2. Then again, bromine, and we end it in IDE. Now with potassium and bromine, if we do the cross method, these are both going to have subscripts of 1. So 1 and 1. It kind of ended up looking like a 4, but KBr with these subscripts of 1 and 1. Remember, we don't write those in, they're just implied. To name this, potassium is what we say is the first element present, and we just write out the full name. Potassium is an alkali metal. It can only form +1 cations. Therefore, we do not need the Roman numerals there for the stock system. So potassium, then bromine. Again, we change that ending to bromide. Now let's look at barium and bromine. Barium is an alkaline earth metal. It always forms +2 cations. For the cross method here, 2 goes down to be a subscript on the opposite element, so bromine, 1 down there. So then we end up writing this as BaBr2. How do we name this? Barium is the element's name. We can go ahead and write that out. Again, it can only form one kind of cation, 2+ cations, so we don't write any Roman numerals here. Then we change this ending to bromide. What you're probably noticing now between naming ionic versus molecular compounds is for ionic compounds, we don't include any of those prefixes. So prefixes were only used for molecular compounds. Then for molecular compounds, we never see these Roman numerals here because these Roman numerals are for those metals specifically that can form more than one type of cation. Molecular compounds do not contain any metals. So just noticing a few differences here is going to be important as you're getting used to naming and identifying molecular versus ionic compounds. So here is our final solution to that practice problem. The next topic now, identifying common polyatomic ions, where it gets a little bit trickier now. So we're going to complete the following table. We're told the name of the polyatomic ion, and then we're going to either fill in that or the chemical formula. When these polyatomic ions are bonded to another ion, that's when things get more tricky. But here we're just identifying the name or the chemical formula. So for this kind of problem, we can just look at the table and then fill in these different blanks here. Now the table I'm referring to is table 2.3. Here, for example, chlorate, ClO3-, bicarbonate, HCO3-, hydroxide, OH-. So again, here we're just identifying the name and the chemical formula, but we will talk about writing out formulas and names more when there are polyatomic ions present. We touched on that a little bit already in chapter 2. Table 2.3 continues on to this slide as well. And remember that difference between a monatomic and a polyatomic. So mon, one, mono, one, poly, many. Here's yet another form of the table. This one has acetate included as well. So I don't think that showed up on a previous table from your book. So here's the chemical formula for the polyatomic anion of acetate. These are the same thing here. Note that there's 2 carbons, there's 1, 2 carbons, hydrogen there's 3, oxygen there's 2. Those are the same thing, it's just written as the carbons together or separately here. So polyatomic ions made from several atoms joined together by chemical bonds. For binary compounds that we've been looking at, those are only composed of 2 atoms. So when a polyatomic ion gets involved, we no longer have just 2 atoms present in a compound. For example, barium chloride, this is 1 atom, this is 1 atom. These come together to form an ionic compound of BaCl2. Barium is not a polyatomic cation. Chloride is not a polyatomic anion. One thing to note here is that you will be able to use one 3x5-inch note card with handwritten notes only, so you may want to write down some of these polyatomic ions on that note card. We recall also from previously that this charge is dispersed out over the entire polyatomic ion. So that negative charge is not just on the oxygen, but it's dispersed around, or it's dispersed over this entire polyatomic anion. So that charge there is important. So for this practice problem, it's fairly straightforward. We are finding chromate in the table, writing out the chemical formula for chromate. Importantly, we include that charge there for chromate. We recognize this is the chemical formula for sulfate. Naming anion here is not super necessary, but we do know that sulfate is an anion because it's negatively charged. Bromate is another one I don't know if I saw on the table, so this is another one to know. Bromate is BrO3-. Next, ammonium we've talked about before as well, so NH4+. This next topic here is naming ionic compounds with common polyatomic ions now. So now we have a cation and a polyatomic anion. So cation with a polyatomic anion, we're going to figure out the empirical formula as well as the name. So this flowchart is included for you in your chapter 2 slides. We're going to go through this flowchart now. So let's talk through this left-hand side first. We know ionic compounds are going to be composed of a cation that's a metal, or it's that polyatomic cation that's ammonium. Then the anion will be either a monatomic or polyatomic anion, so negatively charged. For a cation with only one possible charge, so group 1, group 2, or silver, aluminum, cadmium, and zinc, we write the name of the metal first without the Roman numerals. Remember, we don't need those. Then if we have a metal that can only form one type of cation, and it's with a monatomic anion, then we practice this a lot too. We change the ending to read IDE. Now, this important difference here, if we have a cation with one possible charge, okay, we don't need the Roman numerals. We list that metal by its name. Then if that metal is in an ionic bond with a polyatomic anion, we just use the name of the polyatomic anion as is. We don't change it to read an IDE. If it's not already a name that ends in IDE, we just list the polyatomic anion again as is. Now let's say we have an ionic compound again, but this time the cation can have more than one type of charge. Well, we know how to identify those on the periodic table, and we know that those are going to need those Roman numerals. So as part of the stock system, we will indicate the charge with a Roman numeral in parentheses. Then again, if the anion is monatomic, we change the ending to read IDE. If the anion is a polyatomic anion, again, we do the same thing here, that we just use the name of the polyatomic anion as is. Something else that shows up very briefly in chapter 2 is this concept of oxoanions. So there's a pattern that sort of evolves, for example, hypochlorite, ClO-, chlorite, ClO2-. So we're adding an oxygen each time. ClO3-, chlorate, ClO4- perchlorate. These should all be on that table 2.3, so you should have access to all these names already. It's not really crucial to understand this pattern here. So other than chlorine, these other elements can be part of these oxoanions as well, carbon, nitrogen, phosphorus, sulfur, for example. To quickly define this very briefly, an oxoacid is an acid that contains hydrogen, oxygen, and another element. So hydrogen, oxygen, then another element, hydrogen, oxygen, another element. We will get a lot more into acids and bases starting around chapter 4 of the semester. So to solve this, we can also follow that cross method, and we practice this a little bit so far for polyatomic anions. For that cross method, we would take the charge here and make it the subscript on the opposite element. We take the charge here, make it the subscript on the opposite element. Hopefully you notice something right now. We have to put parentheses around this polyatomic ion. This too relates to everything here in parentheses. Now, if this were only just one of those present, for example, sodium plus 1, NO2 minus, you do not need to put parentheses here if the subscript is just 1. So we could just write this as NaNO2. Okay, so if there's more than one of the polyatomic anion, you have to put parentheses around that to denote the subscript. Let's try this one now. So Cr2 plus PO4 3 minus. For the cross method, then 2 would go here. We're going to write parentheses around that right away. 3 minus would go here. So our final answer here should be written like this, very importantly, with those parentheses around this anion, and then the 2 on the outside of the parentheses. The 4 here is definitely inside the parentheses. The cross method here, 1, all of this in parentheses, 2 for our final answer then, since we don't need to include that 1 of this. So definitely make sure you write those parentheses. The 2 is on the outside of the parentheses. So far we have figured out these empirical formulas. So next, to figure out the names, we follow pretty similar to how we've been naming ionic compounds so far. So we list the metal. Here we know cobalt can be either 2+ or 3+, so we're going to need those Roman numerals there. So we write the name of the metal. Because this can form more than one type of cation, we need those Roman numerals there. Then NO2 minus, we could memorize or have it written on our note card. This is the polyatomic anion of nitrite. Okay, so NO2 minus nitrite. Next, for chromium, can this form more than one type of cation? So for chromium here, yes, 2+ or 3+. So we write the name of the metal, then 2 in parentheses, Roman numeral 2, then the name of this polyatomic anion. PO4 3 minus, memorize or have on your note card, that is phosphate. Next, zinc, that can only form +2 cations, so we'll write the element name here. Why can zinc only form +2 ions? Well, we look here on the periodic table. Zinc is a transition metal, but it can only form 2+ cations. These different charges would be another good thing to have on your note card. So zinc can only form 2+, that means we don't need Roman numerals here. VRO minus, this is hypobromite. It doesn't look like bromate and hypobromite made it onto this table, but here, for example, phosphate, PO4 3 minus, so we identified that as the polyatomic anion named phosphate. So now we have successfully named these compounds as well. Note the Roman numerals. And note that we didn't have to change the name of the polyatomic anion. We just read it from the table and we leave it as is. Now on this flow chart, the last part of it on the right-hand side here is on molecular compounds. We know molecular compounds have all non-metals. And for those, remember we use those prefixes like mono, di, tri, etc. And we add IDE to the end of the second element. Just briefly, for some additional examples quickly on molecular compounds and some practice, let's go through these real quick. There's 1 sulfur, there's 4 fluorines, so sulfur, tetra, then we change that ending of fluorine to be IDE. Silicon and chlorine, there's only one silicon, there's 4 chlorines. Again, we change that ending to IDE. We don't put mono in the front here for a first element that only has 1 present. We do include mono for the second element, but again, not out front for the first element. P4O10, there's 4 phosphorus, 10 oxygen, so tetra phosphorus. 10 is deca, but we need to drop that A, so it reads dec oxide. Then going the other way around, carbon disulfide tells us this is carbon with 2 sulfur atoms. Disilicon hexabromide, there's 2 silicon atoms and 6 bromine. And now lastly in chapter 2, just a brief overview of some concepts that are introduced to you in chapter 2. Something to start getting used to is knowing that acids can be found as a substance that yields a hydrogen ion. It donates a hydrogen ion when dissolved in water. For example, HCl, when that is dissolved in water, these 2 ions separate and H plus is donated from this original compound. So if H plus can be donated from this original compound, that means that this altogether is considered an acid. We will come back to acids and bases again later on. This is just to get you started getting familiar with these different terms. Something else as well that we'll cover more is when H plus ions from an acid are in an aqueous solution, so a water-based solution. These combine to form hydronium ions, so you may hear an acid as something that donates a proton, or something that donates a proton to then have these hydronium ions form in water. So we will come back to this. Something else you may be noticing already in the semester is how we denote these different states of matter. So solid, we put parentheses here with an S, liquid, gas. If you see this AQ, this means the solution is water-based or it's aqueous. So AQ comes from aqueous. Then another term we will come back to a lot are bases as well, so acids and bases. A base can be defined as a substance that yields a hydroxide ion. If this wasn't written here, hydroxide, that is one of the polyatomic anions to know. So hydroxide polyatomic anion is OH minus. So bases will form these hydroxide ions when dissolved in water. We're at the end of chapter 2 now. Let me know if you have any questions about any of the content so far. Hope you're all doing well, and I will talk to you next time.